So I'm Shomajit Roy, and it's indeed a great pleasure. I'm from the Department of Chemical Science, IIIT, Kolkata, and it's indeed a great pleasure to introduce Professor Pati, Arun Pati uh, from the Center for Quantum Science and Technology at IIIT Hyderabad. And he's also the director of Quantum Ecosystem and Technology Council of India. He's highly decorated. And before he has been to the Quantum Information and Computation Group at HRI, Allahabad. Before joining there, he was a scientist at Theoretical Physics Division of BRC. And during his tenure at BRC, he was also a visiting scientist at the University of Wales, Bangor. And then he was also on deputation to the Institute of Physics, or IOP, Bhubaneswar. He has broad areas of interest of research, and he has contributed extensively. And his unique contributions include in quantum information, quantum computation, theory of geometric phases and its application. And his most important discoveries are no deletion theorem, geometric phases for mixed state, remote state preparation protocol, and so on. So today he will be talking about quantum speed limit for states and observables. So with this, we are honored to welcome Professor Pati, and Professor Pati, please.
So thank you for your kind introduction. So can you see my screen?
Yes, we can see your screen, Professor Pati. Okay. Yes.
So again, thanks to Professor Panigrahi and all the organizers for inviting me to this event. So I could not come, but I will continue with this, my online presentation. So today I'm going to tell about some of our recent work on quantum speed limit for states and observables. So currently I am at Center for Quantum Science and Technology at IIIT Hyderabad. Okay, so here is my brief outline. So I will give a brief introduction to this topic, and then I will talk about quantum speed limit for states. And then I will talk about something recently we did about finding stronger quantum speed limit, which goes beyond the standard Mandelstam term kind of bound. And then I will talk about quantum speed limit for observable. This is something new we have done last year. And then I will talk about some applications like in quantum battery and few other things. And finally, I will try to summarize. So we all know that quantum mechanics has several inherent limitations, and some of these limitations could be either operational or could be dynamical limitations. So from a dynamical point of view, quantum speed limit in short QSL has played a pivotal role in quantum computing, quantum control, even quantum thermodynamics, quantum battery, and many more directions. So these limitations are not only crucial for theoretical understanding, but also have a practical applications, practical relevance, as recent years have witnessed the rapidly developing field of quantum technology. So as you can see, whenever we talk about controlling your quantum system, one of the main question you would like to address is how fast you can evolve the your system from some initial state to final state. It could be in quantum computing or even quantum control or quantum target detection and many more things you can think about. So essential question that we want to address in this quantum speed limit is how fast can a quantum system evolve in time? Okay, so quantum speed limit essentially defines the maximal dynamical evolution speed of the quantum system. It determines the minimal dynamical evolution time required for a quantum state. For a quantum state of a quantum system to evolve from some initial state to a target state or final state. So this question was actually answered long back by Mandelstam and Tom in 1945. Over last 20-30 years, a lot of development again, revival of interest has taken place, and a lot of things happen over the last 20 years or so. So to answer this question, you can look at the something to do with geometry of quantum evolution. So we know that given a quantum system and given some Hamiltonian, we know how it evolves in time. But if you want to study the geometric aspects of the quantum evolution, then you can look at the so-called quantum state space corresponding to a quantum system, which is essentially the projective Hilbert space that we define from the Hilbert space of the quantum system. And when a system evolves in time, essentially it traces a path on the projective Hilbert space, which is typically called quantum state space. And once it moves in time, you can ask the question how much distance the quantum state has actually traveled. Sorry, there are a few typos here, but yeah, please forget that. So essentially, you will notice that the distance that the quantum state travels in the projective Hilbert space is connected to the integral of the fluctuation of the Hamiltonian up to the factor 2 over h bar. So you see, it is not just the Hamiltonian that decides the dynamics, but it is actually the fluctuation or the uncertainty in the Hamiltonian that tells you how fast the system evolves and how much distance it has moved away from the initial state during the course of the time evolution. So once you have the distance, when you have the notion of the curve on the projective Hilbert space, you can associate an instantaneous speed of the quantum system, which is essentially so-called ds by dt. If you denote ds as a distance, then we can define the speed, and that speed is essentially the fluctuation in the Hamiltonian. So if there is no fluctuation, system will completely be stationary. If there is fluctuation, non-zero fluctuation, system will evolve in time. So that is as simple as that. So coming to quantum speed limit for unitary dynamics, as I told, it was first answered by Mandelstam and Tom in 1945, and that bound essentially tells that T is greater than TQSL, which is essentially h bar s naught divided by delta h. So what is s naught? S naught is essentially the shortest path connecting the initial and final point. So essentially you can define, given any initial state psi 0 and some final state, say at some point of time psi t, which you denote as psi of t, then you take the overlap of psi 0 psi t, and you define this s naught where the relation that is psi 0 and psi t overlap, and its modulus is essentially cos s naught by 2. So s naught is kind of the shortest path that will connect the initial point and final point. And delta h is essentially your fluctuation in the Hamiltonian, which you define in standard way, that is your, I mean, delta square is essentially s square average minus h average square, that quantity. And several years later, in 1998, Magnus and Levitin, they tried to prove a different kind of bound, which is to do with not with fluctuation, but with the actual the average of the Hamiltonian. And that bound is given by h bar s naught by the average of the Hamiltonian h. Some years later, in 2009, Levitin and Toffoli, they tried to prove that if you unify these two bounds by expressing something like a maximum of this or that, h bar s naught by delta h or h bar s naught by the average of the Hamiltonian, you take the maximum of this one, because given the quantum system and given some Hamiltonian, you don't know which one is tight, So you take both and try to see which gives the largest number, That is kind of the maximum you can achieve. So this unified bound, they try to show it is actually tight. So how do you prove this Mandelstam bound? You can prove in two different ways. One is using the starting from the Robertson uncertainty relation for any two non-commuting observables. You start with that, and then you choose one of the observable as the Hamiltonian, and the other one you choose the projector under the initial state. And then you follow a few steps, and then you realize that indeed you get the Mandelstam bound. Another way to realize is using geometric approach, so-called, you define a distance function, which is essentially your Fibonacci metric on the projective Hilbert space. And this approach was given by Anandan and Aharnov in 1990. And I also did something along that direction in 1991. So using this geometric approach, you can also try to derive the Manhattan term bound by observing the simple fact that given any two initial point on the project Hilbert space, the actual distance traveled by the state will always be greater than or equal to the shortest path connecting the initial point and final point. So the total distance S is always greater than or equal to the S naught. So in equality, you can also obtain the Manhattan term bound. And in fact, both the bounds are actually, they're equivalent. They know, they know speciality about this. So both are actually equivalent, but you can do either way. Uh, so coming to this empty bound, over the last several years, a lot of applications, a lot of developments have happened, and then you can ask the question, when can you achieve the saturation? So the empty bound can be achieved or saturated by something called optimal Hamiltonian, which is not always easy to find, given some general quantum system. If you ask the question, what is the Hamiltonian, or what is the Hamiltonian which will drive the system along the shortest path? The answer is highly non-trivial. This typically occurs when the system is in pure state and Hamiltonian is time independent. So in general, the empty bound is loose for non-optimal Hamiltonians. So then you can ask the natural question that is it possible to derive some new bound or stronger version of the empty bound that is more tighter than the original empty bound for non-optimal Hamiltonian? That is, given any arbitrary initial state and some final state, that you can find a new speed limit bound, new TQSL, so that is as close to the actual time the system takes from initial state to final state. Okay, so that's what we did recently, and to prove that, we use one of our stronger uncertainty relation that I proved with Lorenzo Meccone in 2014. So in that paper, we had three different kind of stronger uncertainty relations. So one of the relation, two of the relations were kind of in sum of the variances form, but also we had a form which is also in the product form, that is delta A delta B is greater than this commutator of AB and this quantity plus something else. That is something else is a positive quantity. And as you can see, if you drop this, you get the usual Robertson uncertainty relation. So in that sense, this is a modified version of Robertson, but and at the same time, this is also stronger than the original Robertson uncertainty relation. And that is why this is tighter than the original one. So using this, we will try to prove that indeed you can obtain a new bound compared to empty bound. So the way to derive is again, if you follow the similar step, that is you choose in that uncertainty relation, you try to choose the observable bit of the Hamiltonian, and then you can see that using this equation of motion for the average of the observable, you can have this, and from there you can show that delta H times this vector is essentially this. And for this RT, we define as this object, and by construction, this is real and positive quantity. And now what you do is you choose this A to be the projector onto the initial state, and then the average of the A is essentially the overlap of the initial and final state, or the instant state. And then you can do the few algebra and then try to see what happens. So delta A is essentially this object, and the derivative of this average of the observable A essentially this quantity. And then using this expression, you will find that that the new speed limit bound is given by t greater than h bar s naught by twice delta h plus integral of this rt, this quantity. Because this is positive, greater than equal to 0, this bound is stronger than the empty bound. And also, not only that, also we prove that if the system evolves along this geodesic, that is shortest path, then this term is identically 0. That means you do get back the the result using outbound and the empty bound actually the match. So this is the stronger quantum speed limit or stronger empty bound, you can say. So we try to apply this in a few examples. So I will not go into detail of all the examples, but I will try to highlight one of the example that is to do with stronger quantum speed limit for non-interacting quantum systems. So what you do is consider m number of subsystems initially at time t equal to 0, all in the product state like psi 0, psi 0, and all these m copies. And each of these psi 0 is essentially an equal superposition of all these orthonormal states and any the dimension of the Hilbert space of the each subsystem. And then we consider each local Hamiltonian, which is of this type. It's a very simple Hamiltonian. And then you can see what happens. So this is a homogeneous energy system where every subsystem has energy average, which is given by this quantity. And then if you find out the uncertainty energy, that goes something like this. So essentially square root of m times n square minus 1 up to these factors. And then you can find out, you can find out the transition amplitude for the state, which is given by this expression, and then this transition probability psi 0 psi t is essentially your post square s0 t by 2. That quantity looks like this. And the object RT is very complicated to actually find. So I skip that detailed calculation here, but I try to highlight these two figures here. So here what you do is you try to plot this T by T QSL and T by stronger SQSL. So this T QSL MT essentially coming due to the empty bound, and this is the new bound. And this is the sorry. So the dotted line here is the ideal, that is T by T QSL is 1. And as you see, for different values, so here you fix the number of subsystem, we take m equal to 2, and we try to do this per different dimension, n equal to 2 and 8 and 14, and we find that how that behave with this compared to our new bound. So this T by T QSL due to MT is lying somewhere here, this is for and this is somewhere here, but this new bound is very close to the ideal value, so you see that is really stronger bound. And the same thing we do here, we fix the dimension, but we increase the number of subsystems for again m equal to 2, 8 and 14, and we see similar behavior. So our bound is much close to the ideal quantum speed. In that sense, this is pretty good, I mean, this is almost close to, so you can by estimating this right hand side of the T SQSL, you can actually predict how much time system will take going from initial state to final state. So the next part of my talk, I will try to focus on the quantum speed limit for observables. Essentially, over all these years, what we've been doing is we're trying to answer the question about the dynamics of the system and time evolution in the Schrodinger picture. Because we know that in Schrodinger picture, the state of a system evolves in time, and the QSL describes how fast the state of a system evolves from an initial state to a final state. But if you go to Heisenberg picture, we know the state don't evolve, whereas observables evolve in time. So then the natural question comes to mind is how fast your observables evolve in time. And quite surprisingly, this was not even answered for over so many years. So this we did last year. So let me focus on that. So in quantum mechanics also, you will notice that during arbitrary dynamical evolution of quantum system, we often encounter a situation where time evolved state becomes perfectly distinguishable, like here, to the initial state. At the same time, the average of physical quantity do not change or change at a slower rate. And another motivation for studying this QSL for observable is the following, that this can help, or this can have applications in understanding the operator growth in many body physics. So what it means is that in the context of complex quantum systems, one of the pressing question is to understand the universal operator growth hypothesis. The observable of a system, which may be represented by a simple operator, tend to grow over time. That is, they become more and more complicated as system evolves. So you start with simple operator in a many-body physics system, and then as time goes, this operator becomes more complex and so on. So we like to see how fast this complexity grows in time. So the observable speed limit is essentially trying to answer the question that the maximal rate of evolution of average of physical quantity during the dynamical evolution of the quantum system. And it will establish a limit on the minimum time, evolution time necessary to evolve between different expected values of a given observable of a quantum system. So how does this look like? Essentially, you start with the so if you want to derive the observable quantum speed limit for unitary dynamics, essentially you start with the Heisenberg equation of motion for some observable. So we have IH bar dO by dt is this commutator, and H is deriving Hamiltonian. And from this equation, if you take the average of this equation on both sides in the initial state and apply this uncertainty relation, you will obtain this equation essentially. And that will tell you that T is bounded by H bar by twice delta H and integral of this quantity. And this whole thing we denote as TQSLO, and we call this as quantum speed limit time for the observable. So from this, you can say that T is greater than TQSLO, and hence this gives the minimum time that the system will take, or the observable will take from evolving from initial to some final value. And for some special case, you can obtain very simple, nice looking form, that is the observable speed limit for unitary dynamics and for self inverse Hamiltonian, observables. That is, if you post very same as identity, then you can express the bound something like this. But even then, sometimes it is hard to compute, so you can obtain different kind of bound, which is given by T greater than H bar by this factor, and then average of the OT and O0 and its magnitude, and divided by this Hilbert Swiss norm. And similarly, you can also derive different bound given by operator norm and trace norm also. What is more interesting is that we found using this relation, you can actually obtain the empty bound. That means you can say that the quantum speed limit for state is actually a special case of the quantum speed limit for observable. So how do you see that? So consider a system initially in some state which is prepared, in some superposition of the eigenstate, and you choose our observable to be projector. That is, you choose O0 HP, and then the probability of finding the system at time t equal to 0 is essentially your mod A square. And that if you measure the projector, you will find this probability that system is initial state. Now, you want to obtain speed limit for the projector, probability of finding system in state I changes in time. So using that equation, you can show that this T greater than this H bar by delta H in this integral of this object. And if you simplify this, then this quantity essentially becomes this object, sine inverse of this, and then minus this, and modulus of this object, this quantity. Now, if you say that initially this system is in state, say, one of the eigenstates, say I, then P0 is 1, and then the above inequality will yield the Mandelson term bound, that is T greater than H bar by delta H times this factor. And this is essentially what we had before, that is your S0 by 2. So that's how you get the T greater than H bar by twice delta H times S0. So you see, in a very simple way, you can derive the empty bound from this speed limit for the observable. And then we try to derive the speed limit for open quantum system dynamics. That is, if your observable, if your system evolves, is not a closed system, evolves by through some interaction with the external world, then we know that you have more general kind of dynamical evolution, which could be Lilbertian, it could be CP-map or something else. So time evolution of observable, if it is given by the Lilbertian master equation, then you can write dO by dt as this very early Lilbertian. And then using again this Scott's inequality, you can prove that d by dt of O average modulo is bounded by this object, and then you can say that the t greater than this quantity, and this lambda t is essentially this average of this object, and then you can denote this as the evolution speed of the observable for the open system, and then this whole thing you can say t speed limit for the open system dynamics. To illustrate a simple example, we considered a single qubit system undergoing pure dephasing channel dynamics. Then this Lindbergh equation you can write something like this. So if you translate into observable form, we can compare how much time is predicted by our bound and how much predicted by the usual speed limit by the state. So this was already done by Del Campo in 2013. They tried to obtain the speed limit for one system dynamics using state, using the state change, and that bound looks like this. So the if you plot the figure, so their bound is something like this, whereas our bound is almost tight. So it is very close to, if you plot this t QSL by t, almost like this. So our bound is much better than this, what they have obtained previously. So as one more application we try to do in the context of quantum battery. Quantum battery has attracted a lot of attention over the last several years, and this was first proposed by Elick and Fens, which are essentially microscopic energy storage devices, and you can charge, you store energy, and you can use the stored energy to reveal. And several theoretical work have been done to strengthen this novel idea of quantum battery and enhance its non-classical features using quantum coherence or entanglement or even quantum discard and so on. So quantum batteries can easily outperform classical batteries because of several quantum advantages. And the quantum battery consists of many quantum systems with several degrees of freedom in which you can deposit or extract work from it. So consider a quantum battery with Hamilton HB, and it is charged by some charge Hamilton like SC, and then total Hamilton is essentially HB plus SC. Then you can define the amount of extractable energy from the quantum system by unitary operation, essentially the ergotropy, which is the average of the Hamiltonian at the time t minus the average of the Hamiltonian state at time t equal to 0. And the psi 0 psi t are the initial and final state of the quantum battery while charging. So using our speed limit bound, you can say that you can answer the question, how much minimum charging time you need to charge your quantum battery. So essentially that is given by this expression. And if you use the other expression, you can obtain also a different kind of bound, which are essentially given by the operator norm or Hilbert space norm or trace norm. And they in particular have a specific ordering, and then you can see which one maximizes this. So now I will try to tell how our speed limit for charging actually answers the correct charging time. But if you use the speed limit for the state, you miss the point. So, previously, what people have done is they obtain bound on charging time of quantum battery based on the distributed the initial final state of the quantum battery. Whereas the bound we have presented are based on the difference of the initial and final ergotropy of the quantum battery. Therefore, our bound can easily outperform previous bounds, especially when the batteries have degenerate energy levels. For example, if you I heard another one, this is different place. Okay, so see that consider a simple single qubit battery with Hamiltonian HV as sigma z, and let us consider the battery initially in the state say A0 plus B1. Okay, and if you look at this expression for agotropy, this is non-zero agotropy, and then if you apply some charging Hamiltonian, and you can reach some final state say A0 minus B1. But if you look at this HV and the initial state, final state, and look at the expression for agotropy, you will realize that you can neither extract work from the quantum battery nor store any work in the quantum battery because both the initial and final state have the same agotropy. So if you use the standard quantum speed limit like empty bound and calculate the charging time, you will obtain a non-zero minimal charging time, which is giving a wrong impression. Whereas if you use our bound, this will tell you that yes, the charging time is actually 0. That means this actually yields the correct minimal charging time. So this simple example actually tells you how good is this bound, So okay, so as one more application, we try to apply this observable speed limit for two-time correlation function. So given some quantum state rho and some observable A0 and AT, we define two-time correlation like this. For closed system, you know that system observable will evolve like this, and for open system they evolve like this. Then you can obtain using our method, you can obtain the speed limit bound for the change in two-time correlation function, which are given by this kind of expressions, and also by this expression. Also, we try to connect to Lieb-Robinson bound in many-body context. So this Lieb-Robinson bound essentially is a bound which provides the speed limit for information propagation about the perturbation. That is given two different observables at different distinct regions of space-time. At time t equal to 0, they may commute, but at time u holds, the observable gets more and more complex, more complicated, and they spread, and then at later time t they may not commute. So this gives an upper bound for the operator norm of the commutator of A, T, and B, where A and B are specially separated operator of many-body quantum system. So what this bound tells you that even in non-relativistic quantum mechanics, one has some kind of locality structure analogous to the notion of finiteness of the speed of light in the relativistic theory. So this Lieb-Robinson bound is essentially given by this the operator norm of this commutator is bounded by this c times some constant times the exponential of this object, and this A and C are positive constants, and this V in this context is known as the Lieb-Robinson bound, or sorry, velocity, and D is the special separation in two different sides. So you can try to connect to Lieb-Robinson bound. So now what you can do is you can derive a distinct speed limit bound for the commutator of A, T, and B. That is how fast the commutator changes in the Heisenberg picture. So if you define the commutator of two observables into different region of many-body quantum system, something like this B0 and AT, and you define this as O of T, then we know how this will evolve. Then using our prescription, you can find that T is bounded by this quantity. So this will essentially tell how much time that the system takes, from initial commuting observable to non-commuting observables. Similarly, you can also obtain this bound also. Okay, so I try to summarize now. So what I try to tell you is that quantum speed limit for states have been there for last several years, several decades, and that plays a very fundamental role in quantum theory, quantum computing, quantum information, or even quantum control and quantum thermodynamics. Many different areas. And what we try to do is we try to prove a stronger quantum speed limit for arbitrary unit evolution, and we also try to apply in variety of examples. And I try to highlight one example where the stronger quantum speed limit is actually very tight compared to what ideal scenario would be, to the actual ideal scenario. And obviously, this empty bound, this is a special case of the stronger quantum speed limit. And then we try to prove quantum speed limit for a general observable, for unitary dynamics, and for open system dynamics. And then I try to also convey that the standard quantum speed limit like empty bound can be viewed as a special case of the speed limit for observable. And then I tried to also highlight that the speed limit for observable can be used to actually determine the minimum charging time for a quantum battery. Whereas if you apply the usual speed limit for state, you may fail to capture the charging time. So I tried to highlight a few things, but there are many more applications. And future, I think a lot of opportunity, a lot of openings are still there. But yeah, so I just stop here. And here are my collaborators. So I had one project student, and then I had my PhD student who is now postdoc at Mohali. So these two, I did these two works, So thank you. And if you have any question, I will be happy to answer.
Thank you, Professor Pati, for this very nice lecture. Now the platform is open for questions. So please. Okay, any questions or comments? Okay, Professor Pati, I have a very simple question for example, like when you are talking of quantum batteries and you are essentially correlating the microscopic states or with the macroscopic states, right? So how does one take care of the statmech part in between? Number one, and number two is how can one think of, or how can you suggest an experimental platform where at least these charging times can be perhaps tested?
Yeah,
If
so
at all possible.
in the second part, I think already there are preliminary investigations about design of quantum battery using photonic setup, even using ionic setup. So I think still we don't know which platform will be better, but I think it will happen in a couple of years. And coming to first part of your question, we don't need really go to macroscopic system. So you can even think of a quantum battery that at single qubit level or 2 qubit level. So there is also you can manipulate easily and you can handle it. Don't go to really macroscopic or statistical mechanic description.
Okay. Thank you. So any further questions or or comments or any clarifications from this nice talk by Professor Pati, please? The students are especially encouraged.
I have two questions, clarifications. Can you hear me?
Yeah.
Yes, please go ahead.
Okay.
Please.
Thank you for your talk. First question is, any reasons why special variables are not considered in quantum speed limit? Because diffraction may impact on the amplitude of the final state.
I'm not getting. So what is your question? Why I'm choosing what?
Special variables, X, Y, and Z, for example, diffraction.
No, how did I choose X, Y, Z? Which example?
Yeah, I mean the diffraction space coordinates.
No, I have not used any. I have not used any different. Any X, Y, Z coordinate. I have used in quantum battery. I have used spin Hamiltonian, and in other cases I have used commutator of two different observable, and so on. So why did I use X, Y, Z? I have not used
because
any.
in space, when your wave packet is propagating in the atmosphere or in the space, then you have to consider also X, Y, and Z.
Oh, okay.
Yeah. So in this case, diffraction may impact on the amplitude of the final state.
Okay, sure, yeah.
So any reasons why you are not considering the spatial
No, you can consider. No, you can consider. I mean, the empty bound. Forget about the new bound. Even in empty bound, what you're given is the given initial state at time t and final time at some capital time t. You can also talk about the wave function at some x and t equal to 0, and then some other x prime and time t equal to t. So you can talk about how it evolves in space with all this diffraction ongoing and all the amplitude whatever changing, and then you can modify your Hamiltonian and then find the fluctuation and find the overlap, and everything will apply. So you can do the same analysis and sorry, you can use the same formula and apply in your context. So no issue.
Okay.
Yeah.
Second question is clarification. In one of your slides, you mentioned about operational and dynamical evolutions. So what is the definition of operational?
Yeah, operational limitations. I mean, if you look at the quantum mechanical description of a system, single system or composite system, and if you just restrict to the kinematic structure, essentially at a Hilbert space level, you know there are other kind of limitations, like you cannot copy a quantum system, you cannot delete, you cannot do this that, those kind of limitations I was trying to refer as operational limitations. So, and the dynamical limitations come essentially to the evolution, change in dynamics and so on. So just wanted to make a distinction between different kind of limitations to talk about in quantum information. So yeah, I did not tell about what operational mean, but yeah, essentially I meant that. So the different kind of limitations you have, like no cloning or all these limitations. So
Okay, it's clear now. Thank you.
yeah.
Thank you. So if further comments or questions, please. Okay, so I guess there are no more questions. Please join me in thanking our plenary speaker for today, Professor Arun Pati, and I would now request the organizers to take over. And I thank them also for the opportunity to chair this very prestigious lecture. Thank you, Professor Pati, and thank you.